So, we have been discussing superconducting quantum interference devices which are written as Squids. S for superconducting, U for quantum, and I for interference, and D for devices. So, we have said that that there are two kinds of Squids depending on the number of Josephson junction and based on how they are driven or what kind of current that is input into the system. So, they are called as one is called as the Rf Squid, radio frequency squid. All of you know that the radio frequencies actually range over very large frequencies. These are like 10 to the power 4 to about 10 to the power 12 frequencies, hertz of frequencies. So, these are called as the radio frequencies. So, one is called as the Rf Squid, and this typically has one Josephson junction and driven by an RF current. And two, of course, what are known as the DC squids, which are most commonly available in for commercial purposes, as well as the discussions are more abundant in for the case of DC squids. Here as opposed to the RF squid, there are two Josephson junctions and two the driven by a DC current. So, let us include very brief discussion on the RF squid, though we will mostly consider DC squid for our purpose. So, all right. So, RF squid. So, schematically it is shown as this is a superconducting loop with a single Josephson junction. So, this represents the cross represents a Josephson junction. And this is the squid loop, and this is inductively coupled to a tank circuit. The word tank means something that can store energy, just like water tank that we know that can store water. So, this is the tank circuit, which is a LC circuit. So, there is a L, let us call it a LT, T for the tank, and there is a capacitance there, and this is driven by the an RF current. There is a RF current that flows into this circuit, and so there is a output which can be obtained from here. So, this is that output. Okay. So, LT is the inductance of the tank circuit and C is the capacitance. So, basically it is a LC circuit and so on. Okay. And this is called as a resonant circuit, or it is called as a tank circuit, as we told. Okay. So, so the tank circuit is driven by the RF current, while the squid loop, which is at the left and drawn here, is inductively coupled to the inductance LT of the tank circuit. Okay. And the resulting RF voltage that we pick up from here, from this point, shows an oscillation with the input current or the flux in this sawtooth manner and so on. So, this could be either you call it the input current or you can call it the input flux, and this is the output voltage. So, it has a sawtooth wave pattern with a period which is given by the flux quantum. So, phi 0. So, please distinguish between the capital phi that denotes the flux quantum or phi 0, phi denotes a flux in general a flux, and a small phi that is related to the phase of the condensate wave function for the superconductor. So, we see a sawtooth wave pattern. So, any change of this flux that is induced into the squid loop would show up in the oscillation pattern, and we would know that there is a change in the magnetic field or the magnetic flux. In fact, it is a misnomer because there is no quantum interference takes place, but it is the first squid to be made probably around but by Zimmermann and co-workers probably around 60s, not too sure about the time. Let us come to the DC squid, which is the most important part of the squid study of squids, and as I said that they are most commonly available in for commercial purpose. Okay. So, again there are two Josephson junction as told, they are connected in parallel, and these Josephson junctions are shunted with a resistance, and this shunting is for the purpose of avoiding hysteresis effects, or it is also to the mismatch of the Josephson junctions by with a great degree of accuracy. It is also possible not to use the shunt resistance and have a sort of mismatched junctions in DC squids, but that gives a much lower efficiency than the shunted junctions. There is an inductive coil that is coupled here, which has already been told. So, this is the input coil, and so there is a DC current source which feeds current to this, and the current that is fed or the bias current, let us call it, which is twice of IC, where IC is the critical current that we have discussed. So, this is a DC current source. Okay. So, there is a current that flows in, and there is an output coil which is the feedback coil or the modulation coil. So, just to remind you that these arms, let me draw it in a different color so that you. So, these arms are basically the superconducting wires or superconducting specimen, this one and this one. They are represented by the condensate wave function, let us say given by psi 0 exponential I phi 1, and the other one is represented by psi 0 exponential I phi 2, and where phi 1 and phi 2 are the phases of the wave function, and ideally no current should pass through this junction classically, but however we know that the current cannot be discontinuous. So, current actually flows through the junction, and not only that, the current actually fluctuates with a very large frequency. We have seen that for a microvolt of biasing, bias voltage, there is a large fluctuation of the order of 10 to the power 12 hertz or so that kind of a fluctuating current that flows through the Josephson junction. So, neither of these circuits, the input coil or the feedback or the modulation coil, they are actually wrapped around the squid, but they are inductively coupled to the squid. So, that is the main idea. Now, if there is a change in the magnetic field that passes through the this loop of the squid, then there will be a change in the output voltage detected, and this modulation. So, this actually the output voltage, as we have just seen for the case of Rf squids, that these voltages, output voltages are periodic functions of the flux, and there will be and the flux, the periodicity is in units of phi 0, which is a flux quantum that we are very well aware of. And if there is a change in the magnetic field through the loop of the squid, the modulation profile changes, and hence we understand that that there will be there is a change in magnetic field, and there are various examples or applications of this. We will not get into those details, but once again, just to come to this shunt resistances, there are two junctions which need to be matched within a few percent, and these shunt resistors actually help in achieving that purpose. And it is also biased with a current which is twice of IC, where IC is the critical current. And so, these are sort of so as there is a change in phase. So, if there is a change in magnetic field or a magnetic flux that flows through this that flows through this loop, then this will be this will induce a phase change in the condensate wave function, and that enhances the current through one of the arms of the squid. So, there is one arm on the left and the other arm on the right. So, one will get a current slightly larger, which is IC plus IB, and the other will get a slightly lower current, IC minus IB. So, as the this output as the flux, external flux increases or decreases through the loop, the voltage will change in a periodic manner, as we have said, and the period being the phi 0, which is the flux quantum. So, that is the main idea of this DC squid, and the most DC squids are mostly used commercially. Okay. So, let us do the DC squids with a little more elaboration and see that the expressions that we get for this. It is more useful for us to redraw this DC squid, not in the form that we have drawn, the circular form, but it is just convention, or rather it is for my own convenience that I am drawing this squid as. So, there is a current that is coming in, and so there is this, and okay. So, this is my all right. So, these are the Josephson junctions, the tunnel junctions, okay, which are by this dashed portion that is there. Let me name them as A, B on either side of the junction, and there is a C and a D. The input current comes I, which we have discussed, that it's twice of IC, and the current actually goes out like this. And we are going to draw a coil. For that, let me take a different color, maybe a red color, and show a contour like this. Hope you can see the red colored contour that we have drawn all across the Josephson junctions. So, these places are the superconductors, let us call it a. So, let us go back. So, these are the portions, let me show a highlighter. So, these are the superconductors on both sides of the junctions, and these are so the dotted line or the contour is drawn well inside the superconductor, and so there is a magnetic field that passes through this loop. So, just distinguish between what I have drawn in the last slide and this one. There was a circular shaped loop that was drawn, and here we have drawn a square shaped loop, otherwise things remain the same. So, there is a flux threading the loop, it is equal to phi. There is a magnetic field which is which is piercing through it. We are seeing the dot of the arrow, which means it is coming towards us. So, there is a current that is flowing, this is equal to I 1, we call it a I c. Let us just write it a little on the left. I c sine of phi 1, and this is a I 2, it is equal to I 2 equal to I c sine of phi 2. So, these are the currents that flow through the Josephson junctions, which are the tunnel barriers, and for convenience we have taken the I c to be same. I c is assumed to be same through both the Josephson junctions. Okay. And so, there is a so the current enters, and the current I 1 goes through the left portion, and there is a current I 2 that goes through the right arm, and that is pretty much it. That is the setup that we are going to consider for our calculation, and this is just an approximation that the I c or the critical current is considered to be same for both the junctions. It may not be, they could be different, and these so these are the red line or the contour lies entirely within the Josephson junction and at a distance which is greater than the penetration depth of the sample. So, our current, the total current is I equal to I 1 plus I 2, which is equal to I c sine phi 1 plus I c sine phi 2. So, this is equal to a 2 I c cosine of phi 1 minus phi 2 by 2 and sine of phi 1 plus phi 2 by 2. Okay. This is just applying the trigonometry trigonometric identity. So, these are that is the total current. Now, the important thing is that the phase difference around the loop is gradient of theta dotted with dl, which is equal to a theta b minus theta a. So, let us just go back for a second to the diagram. So, theta b and theta a. So, it is just a convention that is assumed that so the current is flowing like this. The theta b is at a larger potential, it could be at a larger potential than or the phase than that of A, or it could be the reverse, but we have simply taken it to be the total change in phase dotted with the line integral and over the entire contour is taken to be like this. So, theta b plus theta a plus a theta d minus theta c plus a theta c minus theta b. So, we are here. So, we have so these are the junctions. So, there is a B and there is a, there is a parallel junction which is a C and a D. So, these are so these two are across the junction B minus A and D minus C, and this is C minus B is within the superconductor, and there is also a theta A minus theta D. So, that is the total change in phase, and this has to be equal to a 2 pi n, and which is for the single valuedness of the wave function. So, now let us write down. So, let us write this as equation 1, and we can so write that from the definition of the gauge invariant phases. Theta b minus theta a is equal to a minus phi 1, that is the phase of the condensate. We have just taken it for a convenience or rather as a matter of convention to be like this, and there is a 2 pi by phi 0 and a to b and a dot d l, which is the vector potential. A is the vector potential such that b equal to curl A. So, the magnetic field and the vector potentials are related by this equation. So, that is across the junction, and also across the other junction is theta d minus theta c, is equal to a phi 2 and minus 2 pi over phi 0. Remember this small phi on the first term on the right, phi 1 and phi 2 are the phases of the condensate wave function, while the phi 0 that is written here that denotes the flux quantum. And so, this is again across C to D A dot D L. So, there is a magnetic field that is threading the loop. So, that is because there is a vector potential that is there. So, these are for, so this let us write it for 2, and these are across junctions. And what about the superconductors? So, the superconductors will have theta c minus theta b, which is equal to a b to, definition is b to c gradient of theta dot it dotted with dl, it is equal to a minus lambda l b to c j s dot dl minus 2 pi over phi 0 b to c a dotted with dl. And so, this is one of the things. Remember that this is coming from the London equation. Lambda L is the penetration depth, London penetration depth, and Js dot dl, and then 2 pi by phi 0. This is for the superconductor. Okay. For the junction, of course, this term is not there. And then the other thing is theta A minus theta D, which is equal to the A to sorry, it is a d to a, it is a d to a gradient of theta dotted with dl equal to minus lambda L d to a j s dot dl and minus 2 pi over phi 0 d to a dot dl, and this is across the superconductor. So, we have so let us call this equation as 3. So, if we add this 2 and 3 in order to get 1, then we will be able to write this as, so adding 2 and 3, we can write it as phi 2 minus phi 1, it is equal to a 2 pi n plus a 2 pi over phi 0 closed integral of a dot dl plus a lambda L b to c j s dot dl plus a lambda L d to a j s dot dl. So, this is of course, by assuming that these Josephson junctions have infinitesimal width, and so these are that is the change in the or rather the difference in phases of the condensate for the two superconducting condensates, and so this is equal to 2 pi n plus 2 pi over phi 0. Now, this quantity is nothing but b dot d s by using Stokes law, because it is curl A dot d s, and so this is d curl A dot d s, and curl A is nothing but b. So, it is b dot d s, which is nothing but the flux. So, this is that flux phi, and plus a lambda L over the contour. So, do not so let me just write contour in red color. So, this is j s dot d l. Now, this will be 0 if the contour lies deep inside the superconductor that is at a distance d from the inside of the loop at a distance much greater than the lambda L or the London penetration depth. So, we are landing up with the expression that this change in the condensate phases of the condensate is nothing but a 2 pi n and a 2 pi, and now there is a ratio of phi by phi 0. Okay. So, this is the equation that we need, and we also is important to us, which is we know from the Josephson junctions that there is a relation of this kind. Now, for the total current, the total current I is given by twice of I c and a cosine of pi phi over phi 0 and sine of a phi 1 plus a pi phi by phi 0. So, see that I as a function of phi 1 has got an amplitude which of course modulates, and there is a sine part that goes with it, and let us call this equation as maybe we have called it as 3. So, we can call this as a 4 and maybe this as say 5. And then the flux in the contour so, that is the circulating current. Now, the circulating current, so that is the relationship between, so assuming that there is a self inductance of this Squid circuit or the Squid loop which is given by L. So, that will be the phi, the total phi or the flux would be the external flux due to the external magnetic field and the Li, where L is the self inductance of the loop and I circulate or I circ is the circulating current. So, I circ is the circulating current equal to I 1 minus I 2. Okay. That is the current that is circulating, because they are in opposite direction I 1 and I 2, and L is the self inductance of the coil or the loop. Okay. So, the total flux, so this is the total flux. So, phi can be written as phi equal to phi external and a plus LIC sine of pi phi over phi 0 and cosine of phi 1 plus pi phi over phi 0 and so on for given. So, let us look at this equation and equation 5 and 6. So, this is 6. So, we have for a given external flux which is phi x, which is the first term on the right there. So, there is a range of I and phi that satisfy equations 5 and 6. And of course, one needs to know IC, which is the resistance less current or the critical current that flows into the Squid loop. So, let us just talk about Squid for a moment, Squid without self inductance. Okay. So, for L equal to 0, you have phi equal to phi external. Okay. So, what happens is that your phi versus phi external. So, phi external normalized with phi 0 and this is phi over phi 0. So, that is like a straight line that passes through the origin. Okay. All right. So, this is phi equal to phi external. So, which gives for the total current I equal to twice of IC cosine of pi phi external divided by phi 0 and sine of phi 1 plus pi phi external by phi 0. And remember that there is a relation between phi 1 and phi 2. So, this is also a function of phi 2. So, the extremum of this current, or rather the the maximum. So, let us just write extremum, because we do not know before we take a second derivative whether it is a maximum or a minimum. So, the extremum going to 0 is only saying that it is an extremum, or the function going to 0 says only about the extremum condition. So, the extremum occurs when the only variable is of course phi on the right hand side. For d I d phi 1, it is equal to 0. So, this occurs when cosine of phi 1 plus pi phi external by phi 0 is equal to 0, or equivalently the sign is completely out of phase, as we know. It is pi phi external by phi 0, it is equal to 1 or plus minus 1. So, this gives of course the I max, which comes from the extremum condition, is in fact the maximum here is 2 I c and a cosine of pi phi external by phi 0, and so a plot of this looks like this. So, there is so this and so on. Okay. These are of course of same height, maybe it does not seem so, and it is very symmetric about 0. The drawing is not all that good, but you should it is slightly harder to draw accurate on this panel. So, this is the I max as a function of the phi external or the external flux that is threading the loop, and that has a sinusoidal dependence. So, this is minus phi 0 by 2, this is phi 0 by 2. See that it has an exact period of so this is like this. So, this is minus 3 phi 0 by 2, and this is plus 3 phi 0 by 2, and this of course goes like this. So, this is the so this has a maximum equal to 2 I c, which is shown on the plot on the y axis. So, I is plotted, the current is plotted, rather the maximum current is plotted as a function of the external flux that is threading the squid loop. And so, for phi equal to some n phi 0, n of course an integer. So, also we see a minimum equal to 0 for phi equal to n plus half phi 0. Okay. So, these are the n is an integer of course including 0. So, these are the current variation with respect to the flux, and as we have said a number of times that this variation of current is a periodic function of the flux, and there is a change in the external flux because of a change in magnetic field. There will be a change in this periodic evolution of the current, and also of course of the detected I mean the voltage that is detected in this feedback loop, that also will change and will have a variation like this. So, just to summarize that we have done in this last part of this course, that we have done Josephson junctions, and then how they are applied to the the theory of squids, and how the current variation or the voltage variations are there. And we have discussed briefly that there is a Rf squid which uses one Josephson junction, and DC squids, which are most commonly available, they use two Josephson junctions in parallel and driven by a DC current which is twice of the critical current, and this is that current variation that is shown here. So, just to summarize the entire course, that we have started with basic idea of superconductivity, Meissner effect, and London equations and so on. And then we have talked about BCS theory in details and understood that how a pairing attraction in the electronic channel takes place, which causes pairing, and hence that causes superconductivity. And these are conventional superconductors, so gap equations are derived. And simultaneously we have seen a phenomenological theory of superconductivity, which has been attributed to the Ginzburg-Landau theory, which writes down a free energy functional, minimizes it, and gets various information that are related for these superconductors. In fact, they preceded the BCS theory, because it's a phenomenological theory. BCS theory is a microscopic theory of superconductivity. And then we have talked about flux quantization. We have talked about the new unconventional superconductivity, D-wave pairing, and we have also talked about the non-Fermi liquid features that are very apparent from the experiments in the case of high TC superconductors, which are the cuprate superconductors. And finally, we have seen what are called as Josephson junctions, and how Josephson junctions can be used to make squids, and these squids formed interesting sort of addition to this discussion. Before I wind up, just say one thing about the application of squids. So, basically there is something called the magnetoencephalography. And in short, it is called MEG. So, basically it is done with respect to the brain. And so, as I said that the magnetic field associated with human heart it is about 10 to the power minus 10 Tesla, while the same associated with human brain is about 10 to the power minus 13 to minus 14 Tesla. And as you see that there only squids can determine if there is any change there. So, if you think that each neuron is like a magnetic dipole, so we can calculate using the Biot-Savart law the magnetic field due to such a dipole, which is Q cross R by R cube. So, this is the dipole model. Q is like the like the current or something that is there. So, this is B is about B at R equal to about 10 micrometer is approximately equal to 20 picotesla for Q equal to something like 20 Fermi ampere meter. And this is when this the neurons become more active, and it becomes like something around 100 Fermi ampere per meter. This becomes something like 100 picotesla for Q to be equal to about 100 Fermi ampere per meter, and so on at the same distance. This is roughly an order of magnitude. So, this change can be detected by this MEG technique, and suppose there is a trauma that a patient is having at the brain, and then this is the kind of change in magnetic field that would be recorded, and the only instrument that can record it is a squid. So, there are various other applications of squid which we are not getting into details. So, these are the sensory applications and all that. So, by and large this is where we should stop and maybe sort of take a review of various things that are or rather I mean the study of superconductivity does not stop here, and there are lots of other directions in which studies can be can start, and we of course hope that with this introductory course you would be able to build upon various things related to superconductivity. The field is still very open, and lots of research is currently going on.